construct an inclined plane. Inclined plane is a plane which is, in fact, inclined. Okay? All right. If you don't know what the word incline means, well, you're probably living in the wrong town. I'll note the following. If I start to raise this up, at some point, what's going to happen, Mr. Leoncio? How do you know that? Experience?
Yes.
There's a lot of friction right in the middle of my inclined plane. I probably should flip it over. Somebody put a lot of tape right in the middle. Okay, so let's try this again. If I raise this up, eventually get to a point where it slides down the inclined plane. What force make it go down the inclined plane? Gravity. Force of weight. I like that better because I said stop using gravity. Now, force of weight is making it go down the inclined plane. That's in fact true, and I'm not even going to disagree with you. But I'm going to say, you're wrong. What? Nice. That made no sense at all, Mr. Anthony. You're lay off the caffeine. Okay. Here's my question. Which way does weight operate?
Straight down.
Straight down. Which way did the thing go? It accelerated that way, which means the force that pushes it down the inclined plane can't be just weight. It can't be. Because weight operates straight down, and that did not go straight down. An object going down an inclined plane does not go straight down. What's the other force, man? What's the other force? We have names for forces. Give me one.
Acceleration.
Mr. Yontail, what do you got?
Force normal.
Force normal. Now think about it. Now I've got my inclined plane like this. Force normal is going to operate which way?
Down.
Normal to the surface. And this component is going to make it go down that way. Right? It's the plane itself that pushes it sideways down the inclined plane. Which leads to a number of problems because it's not going in a normal X or Y direction. It is going down the inclined plane, which makes the math really messy. So starting out, I'm going to go back to my inclined plane, which is sitting right here. I'm going to draw the real forces on it. The real forces on it would be force of weight pushing down, force of normal pushing that way. Now for right now, I'm going to ignore friction, but friction plays a huge part of this. But just give me a second while we sort out pretend like it's frictionless, and we'll still have a good problem here, right? Now, it accelerates this way, right? It's darn inconvenient that this force is pointed the wrong way. So what we're going to do is we're going to cheat. Okay? We're going to say, look, I don't like the fact it's pointed this way. It makes my math really, really hard. So what I'm going to do is I'm going to break it into components. I'm going to break it into a component this way and a component this way. And I'm going to make a little right angle in this corner. Okay? And now I've got into the board, which I'm not going to care about much because what goes into the board, I don't care. It's not going to accelerate in that direction, so that's wasted force. Gone. The board's going to push out. In fact, this force here is going to equal to the force normal. Agreed? I think my pen is off. So force, this is going to be force. Now I need a name for this. I'm going to call it force perpendicular. Now is this a real force?
No.
Yes.
No!
How is it not real?
It's a component. It's a piece of the force, right? It's how hard the rope pulls this way in the other diagrams, right? It's not really pulling that way, right?
Right.
This is real. This is force of weight, right? Okay. What about this force down here? What are we going to call it? That's force perpendicular. This is to the inclined plane. What are we going to call this one? Force parallel. We're going to call this component force parallel. And we're going to note now that if it's a frictionless environment, what's the only piece of a force that's making it go down the inclined plane? The force parallel. So if I can just figure out what force parallel is, I'm done. MA, right? Golden. So I need this component. Now to do that, I need to do some geometry, and we know we're all very strong in geometry. But this is not a tricky one, so let's see if you can do it. This is a right angle, right?
Yes.
I'm going to have an angle down here. Agreed? Now that angle plus this angle plus this angle have to add up to what? 180. If that's true, then these two have to add up to 90. Now, this is drawn directly into the inclined plane, right? So if this is drawn directly into this must also be 90. So if that's 90, then this angle and this angle add up to 90. Then this angle and this angle must add up to 90. Then what's true about these two angles? They're the same. Okay?
Wow.
All right. Now, without much further ado, I want you to try problem number 1. Get as far as you can. You're going to get stumped. Try it. Or you might not. You might be able to, at this point, you have enough. You can do it. It says, by the way, mu equals 0. It means there's no friction. And then it says the acceleration equals question mark. That means that I'm asking what's acceleration. That's our notation for it. Give me the problem. Got force of weight pulling straight down.
So that's the force.
Redford, up here. Force of weight pulling straight down. It's a 200 kilogram object. So how heavy is the? Sorry, how heavy is it?
1960.
200 times 9.8, right? Okay. So that's going to be 1960 newtons. Now I'm going to break it into components because that's what's going to be useful to me, right? I care about this one. I know this angle is the same as this angle here, right? So I can solve for what this force is. So force parallel is going to be equal to, so I go, what would it be? It would be sine of 45 degrees is equal to force parallel divided by 1960, right? Put that in my calculator at 0.7071 equals force parallel over 1960. What was the outcome question?
1385 newtons.
Okay, you're way ahead of me.
Why? Force normal. I don't know why I started. Force.
Fine.
And I got 1960.
No.
What's the force normal?
Force normal is equal to this piece here. Whatever that is. I haven't even solved for it yet.
Isn't force normal just weight?
No. Welcome to the part where it stops becoming weight. No. The board is no longer pushing straight up to hold it in place. The board is shoving this way just to keep it from going inside of it. Remember, you told me weight's pushing it down the inclined plane, right? Is it supporting all the weight then? Not anymore, right? It's only supporting part of it.
Okay.
This is the part it's supporting, right? Just keep it kicking it out of the board.
Yeah.
Right? So these two balance out. This is what's left over, which shoves it down the inclined plane. Okay? All right, so now that I know the net force, so now I'm going to go what? I'm going to go F net equals the sum of all the forces. Agreed? MA is therefore equal to the only force on it's force parallel, right? Agreed? Pausing there, Redfern, you with me?
Why?
What?
Why? Is that the only force?
What other forces are on there? I've got force normal and force perpendicular. Those balance out to 0, right?
What about force friction?
Okay, we said no friction so far because mu is 0. This is an incredibly icy surface.
But,
It won't be 0 for very long.
yeah.
It's all going to be 0 for one whole problem, and then we're going to add it in on the very next problem. I promise.
So then, yeah.
There's reality that's there, right? Yeah. How many perfectly frictionless surfaces have you run into? Not many. What's the mass? 200. So I got to solve for acceleration.
Six.
6.9, I think it's 3, right?
Yeah.
Meters per second squared, and there's my answer for how fast it accelerate. Now, Miss Redford objects to this problem. She objects on the basis of what? There's friction. There should be friction in the problem. The answer is yes, she's right. Now listen. How does friction going to mess up my perfectly good problem? It's going to add a force in which direction? Up the inclined plane, right? Up the inclined plane. It gets worse than that. Because what's the formula for friction? Mu force normal. Well, how am I going to find the force normal? That's how hard the board is pushing out this way. So how am I going to find that? It's going to be equal to what? It's always going to be equal to this, right? So I'm going to solve for this, and that's going to be equal to force normal. Okay? And then I'm going to take my force of friction. Everybody watching? I'm going to drop it right here to the sum of all forces, and it's going to go right there. Okay? Because you're going to have two forces on it now. All right? Try the next problem. See how it goes. So you break into those two components. So we're moving forward. Now I'm going to go F net. Is the sum of all forces. Agreed? MA is therefore equal to, what are my forces? I got force parallel pushing me down the inclined plane. I got force of friction telling me, nope, not going down the inclined plane. Agreed? So now my mass is 200. My acceleration is, I don't know. My force parallel is 980 minus force of friction is mu force normal. Mu is 0.40. Force normal is this same as the force perpendicular, right?
Yep.
This becomes 1697. Wish I could write. That would be cool. 1697. Oh, good. Dyslexia on top of it. All right. Awesome. One more disease to have. Minus 0.4 times 1697. And I get 301. I get 200A equals 301 divided by 200 is about 1.51, I hope. Meters per second squared. Agreed? Can do it. That's how they're done. All right, let me pass out a worksheet, give you a bunch of these to practice. Get started right away. We'll do a couple of them on the board, then I want to start the next topic because this is going to be part of your homework.